Hello everyone. Myself Lokesh Sharma. I am from group 317. Today's my topic is Bernoulli equation. So Bernoulli equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It is essentially describe the relationship between the pressure, velocity and elevation of following fluids. It has countless applications. We can use it to explain how planes generate lift or to calculate how fast liquid will drain from a container. Like, for example, we will explore these applications and a few more later on. But let's study reviewing the equation itself. It was the first published by the Swiss physicist Daniel Bernoulli in 1738 and it looks like this. This is the Bernoulli equation. This equation states that the sum of these three terms remains constant along a streamline. Each of the term is a pressure. The first term is the static pressure, which is just the pressure P for the fluid. Then we have the dynamic pressure, which is a function of the fluid density rho and velocity v and represents the fluid kinetic energy per unit volume. And the first term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration and h is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation is a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is the really valuable information that can help us analyze a whole range of fluids flow problems. This equation does have a few limitations which will be covered later on this video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline is a steady flow as the path traced by a single particle within the fluid, or more technically as a curve that at all points is tangent to the particle velocity. Let's look at an example where we apply Bernoulli's equation. To flow through a pipe which has the change in diameter, we want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations. So we can rewrite like this with 2 points 1 and 2 both being in the same streamline. There is no significant change in elevation between points A and 2. So the potential energy terms cancel each other out and we put all the statics. Pressure terms on each side, we get this equation for the change in pressure. If we assume that the fluid is incompressible at the mass flow rate at points 1 and 2, of the conservation of mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area A2 is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. This is quite intuitive. By substituting this equation for B2 into Bernoulli's equations, we can see that since the velocity increases between points A and 2, the pressure between both points must decreases. This concept that the horizontal flow and increase in fluid velocity must be accompanied by a decrease in pressure is one of the formulating which can be called Bernoulli's principle. It can seem counterintuitive because people often used increase in velocity to result in a corresponding increase in pressure. But it makes sense if we think about the conservation of energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy. Bernoulli's principle shows up a lot of different places. We can use it in the help explain how plane wings generate lift, fluid flowing over, and airfoil travels faster than fluid flowing below it. According to Bernoulli's principle, this creates an area of low pressure above the airfoil and an area of high pressure below it, and it's this pressure difference that generate lift. It will cover lift and drag forces in more detail in a separate video. Bernoulli's principle also explains how Bunsen's curves work. When the gas valve is open, gas flows into the barrel at a high velocity. Following Bernoulli's principle, this high velocity creates an area of low pressure in the barrel which draws air in through the air regulator, allowing is more complete combustion of the gas. Several different flow measurement devices rely on Bernoulli's equations to determine the velocity of a flowing fluid. The periodic static tube is one of such devices. It is often used in aircraft to measure airspeed. How it works? If I place a tube into a flowing fluid like this, and we attach a pressure tube to the end of its meter, will measure the pressure at the end of the tube. At this point, the fluid velocity is reduced to zero, so it is called the stagnation point. And the pressure measured by the meter is called the stagnation pressure. We can apply Bernoulli's equation between the upstream point and the stagnation point and show that the stagnation pressure is equal to the sum of the static pressure. And the dynamic pressure terms, all of the kinetic energy is essential being converted into pressure energy at the stagnation point. We add an outer tube which is sealed at the end. But the holes further downstream, the outer tube will measure the static pressure of the fluid instead of the stagnation pressure. These two pressure measurements gives us all the information we need to determine the velocity of the flow. Now another flow measurement device that uses Bernoulli's equations is the venturimeter, which is an instrument used to determine the flow rate. It works by measuring the pressure drop across a converging section of the pipe. Say we want to determine the flow rate Q, which is the velocity multiplied by the pipe cross-sectional area at the point 1, we can easily rearrange the pressure drop equation. We derived earlier when we looked at a chance in diameter, we get this equation for flow rate. All we need to know this dimension of the venturi, the fluid density and the pressure P1 and P2 are that allows us to calculate the flow rate. The venturimeter has no moving parts and very simple and reliable way to measuring the flow rate through a pipe, and diverging section is longer than the converging section to reduce the likelihood of flow separation and keep energy losses low. Let's look at the one more example where we can apply Bernoulli's equation. Is we can say a beer keg. We want to calculate how fast will drain. First open the tap of the bottle. We all need to do is define our 2 points along a streamline and apply Bernoulli's equations. It's a gravity feed key with a vent at the top, meaning that it's not pressurized. The pressure at both the points will be atmospheric, so the static pressure terms cancel each other out. We can also assume that the key is large enough that the velocity at the point 1 is close to 0 if we rearrange Bernoulli's equations. And define the height between the beer level and the tap as h. We can get this equation for the beer velocity out of the tap. Those were few example of cases we will apply Bernoulli's equation to get some valuable information or the solve a problem, but we use it correctly. It is important to have an understanding of the limitation of the equations which we arise because of how it's derived. Thank you.